Right. To determine cube root of a complex number, in this case, I can refer to the minus 8 as a complex number. That's right. So, because minus 8 is actually the complex number, we can say 0 minus 8i. All together? Okay. So that's a complex number. So if we are to find the cube root of that number, what do we need? We need the modulus of the complex number which is given. Are we together? We also need the argument of the complex number which is given. But for minus 8 is easy. Sometimes when it's easy, I don't really worry about the formula of finding the argument. I just plot my number on the system of coordinates. If I'm not mistaken, minus 8 will be somewhere this side. I'm just choosing some funny scale there. So minus 8 is somewhere there. If I want to represent it as a vector, I can put an arrow there for minus 8, isn't it? So the origin of that vector is somewhere, the tail of that vector is somewhere there, the origin. Now the argument is supposed to be the angle between the positive axis and that vector which determines the number. So the argument is this one. Do you agree, all of us? What is that? What do you prefer to use, the degrees or radians? Okay, let's say now that is what? Pi. Do you agree? So that's the argument. For the modulus of z, then this is x squared, so x squared, which is in this case 0 squared plus minus 8 squared, and we clearly can see that that will give us what? 8. So in this case, let's say the roots now, this is the cube root, isn't it? It's cube root. So we know that according to De Moivre's theorem, there will be k roots. In this case, k is running from 0 to 2. Then we say this will be the modulus. Now is the cube root of the modulus angle, the argument of the number, plus the 2 k pi, all divided by 3. We agree with that one. Then we should indicate here that k is equal to 0, 1, 2. All together. So now we can start computing these roots. Now, say now get z0. This is 2, isn't it? You can just take that as 2. Then z0 will give us this, pi over 3. Now, if you want it in the way we were said we should give given, then you can now write this as 2 cosine pi over 3 plus j, or say 2. Oh, I'll tell you where the j is coming from. The j is coming from my getting used to teaching electrical engineers. They don't want to use I because I is going to confuse them with current. So please correct me when you get there. Right? Yeah. So 2i sine.
Why do you have, can I ask you, why are you multiplying it by 2?
Just hold on. 3.
Oh, it's a 2.
That's right.
Yeah.
There was a slip of a pen also that I wrote in a 2. That's separated. Then that's that for the first one. For k equal to 0. Can we move on?
Yeah.
Is
I
it?
just want to say sometimes you can be given that they say do not express it in terms of cost. Do not leave it in terms of trigonometric signs.
Yeah.
Just like in the assignment.
Yeah.
So
Yeah.
you have to solve it from there.
Yeah. So now if you want this, change this to rectangular form like as in form A plus BI. You need to evaluate these sines and cosine, and then you get particular numbers for A and B. Is that right? Yeah. So that's right. That is if that is what is asked. But if
Always, I think in our examinations, it's always asked not to leave it in trig.
not to leave it in trig.
Yeah, we shouldn't leave it in trig.
Okay, so then you have to evaluate there, and then so this normally this would give in general this would give you decimal numbers. Then also maybe they might say give to so many decimal numbers, round off to so many decimal numbers. Then you do that. That's right. They say if you this one is an easy angle, it's fine.
Yeah.
But in some
mostly,
cases,
I think mostly what the angle that should be, they will give us a special angle.
Special
because
angle.
We're not allowed to use the calculator.
okay, no, that's fine. Then you get a easy one. Okay. So can we leave that on there? What is the what is special angle?
Yes.
What is this? This is 30 degrees, no?
It's 60.
Oh, 60, sorry, 60 degrees. 60 degrees. So what is cos of 60 degrees in there? What's the ratio? It's a half. So if it's a half, it's going to be 1. Because multiply half by 2. Then plus
It will be square root of 3 over 2.
square root of 3 over 2.
I'm not 100% sure.
Let's double check that. Square root of 3 of square root of 2. Square root of 3 over 2.
Yes.
Then now multiply by 2 to be square root of 3. So we've got I square root of 3.
But then you still have the 2. Oh, you've done it.
You have multiplied, yeah. It's not, yeah.
What?
Come again. Which one are you copying?
What you just written.
You want to copy it?
Yes.
Okay. But you're going to get it on a video clip.
Oh.
But you can copy it just to write it so that you can have a feel of it.
Yeah.
Then you get used to writing it. Yeah, I think you'll get it as soon as maybe tomorrow. Right. Are we together? So let's get Z1 now. Z1. Please, guys, I hope everybody we agree or we can follow. How did you get to this state? Is that right? We substituted 0 for k, that make it 0, then we get to a third. Now we're going to substitute 1. We're going to substitute by 1 there, then we get 2 pi. Then
Maybe an easier way is to write the entry formula for them. Because you see, you're using this division thing.
okay, yeah, no, I'll write maybe the general formula at the end,
because I
yeah.
think some of them will
Yeah.
be- I'm not saying anything.
Yeah, but yeah, so it's good. At the end, we're going to write just a general formula so that you can see for any n what do you do. Yeah. So then for 1, we put there, you're going to have 3 pi. Now, if you have 3 pi, they divided by 3, we're going to have pi. Do you agree? So now we're going to have here 2 angle pi. This kind of notation is very easy, handy to when you're working this kind of work. I think that's the advantage of it. Then you come here, you say now 2 cosine pi plus 2i sine pi. Sine of pi is 0, isn't it?
Yes.
Yes. Cosine of pi
Minus 1.
minus 1. So we're going to end up here with minus 2 plus 0i, which if you want, you can give it as a minus 2. Are we together, guys?
Yes.
Please don't remain behind if you are. There's something I'm not sure. Is that correct?
I want to ask.
Yes.
For what's that?
Yeah.
How did we get to and that time?
Which one? This 2. 2 is the cube root of
Yeah. And
this one.
inside of it.
This one. How did they get this? I took 0 here. This formula says substitute 0 here. I took 2 times 0 times pi is 0. 0 plus pi is
Okay.
pi.
Okay. So your friend has to find that formula, the one that you wrote, the ZK.
Okay, I think
Yeah,
just hold on. Yeah, just hold on now. I can see your question. Let's finish this, then we go back to that discussion. I thought you were already familiar with that. Okay, no, that's fine. Right. So now what happens here? Let's get to Z2. Now in Z2, we're going to substitute that by 2. We get 4 plus 1 is 5. So our angle is going to be 5 pi over 3, and still they've got a 2. Then we write it as 2 cosine 5 pi over 3 plus 2 I sine 5 pi over 3. Are we together? So then, after that, I will now leave this to you to go and work out the coordinates,
Yeah.
whichever
But
angles.
it's 60 degrees because you have to reduce it and reduce it.
Yeah, you can reduce it up to using 60 degrees, isn't it?
Yeah.
But actually, this is easy. Once you've got a complex number like this, you should expect the other complex number also to be involved. In this case, the conjugate of this one. So I'm very sure that this one will give you 1 minus I cube root of 3.
That's correct.
Yeah. Normally, there if you know that fact, you can actually quickly just, what you can do, maybe formally you can just manipulate this to 60 just to make the marker see that you know what you're doing. But what you should expect actually is to expect this conjugate of this number to be the one which comes there. Yeah. I don't know, in your theory of complex numbers, somewhere maybe at the earlier course, you might have noticed that if you've got a polynomial which has got real coefficients, if a complex number is a root, the conjugate is also a root. I think in pre-calculus you've got something like that. Okay, so that's how you calculate this. But now, for those who are not very clear with the formula, how do we get to this? Then I think then we need to have a discussion that far. What I'm going to do here, let me just say, let's have something like that. Now, check. Let's check something like, let's say roots of, let's say n roots of complex numbers. Right. What do we do here? Let's say you are having how can I start this thing? Let's go and start this thing. Let's say I just want an arbitrary root n of a complex number. So let's say I'm having a z equals to root n of let's say just a plus b. That j again. Plus bi. Are we together?
Yeah.
Okay. To do this, you need to say you know what I'm just sure of? I'm asking myself, I'm talking to myself whilst I'm trying to talk to you. You guys, have you represented numbers in exponential form? Yeah. You haven't? Okay. So then I'll just keep to that one which you use angle and the argument. Okay. So now listen. Now, what we need here, we need to get the modulus of A plus B I, which let's label it as R. All together. Let's label it as R. Let's see, put this thing as I. Then this is equals to square root of A squared plus B squared. Do you agree? Okay. Then we also need theta.
Why are we taking the I?
Now, when we're calculating modulus,
So when you're calculating modulus,
you don't include the I. Why? Check this. To convince you.
yeah.
To convince you. There is a point there. It's a complex number. It has got this as your X, which is your A, and it's got that distance there as your Y, which is your B. You are reading it off from the coordinate, from the vertical there, and this one you're reading off from there. What is the modulus? The modulus is the distance of that point from the origin. Now, if you look at that story now, what you have there, you've got Pythagoras theorem. You understand what I'm saying? So when you need that distance has nothing to do with I, it's just a distance. That's what we're calculating. So you don't need really to square I. Yeah. Okay. Are you convinced? Okay. So now the argument is this angle. Now for that angle now, you will say now tan second function y over x. That applies in any quadrant. Like now we're in the first quadrant. If this number was somewhere there, or somewhere there, or somewhere there, we need just to work with our angles properly and use the reference angles and calculate the right angle. The correct angle. I'm not saying the right angle is the right angle. The correct angle, and they use it here. All together. So now once we've done this, this number which is inside here, we can now write it as A plus B I is equals to modulus argument theta. All together. Modulus argument theta. Let me do something. I hope we're fine then. So that is example. That's the example. Then what we saw this side is actually how do you arrive at that formula for the sake of those guys who didn't understand it. Yeah, but it's very, very important. You mustn't lose sight of this, that you're going to get n roots there, and this k must always run from 0 to n minus 1. Okay, and then you must know that these roots are actually vertices of regular polygons around the origin. That is important to know. You want another example for this one? Can I challenge you and say, go and let me put this tomorrow? Are you going to be able to get this tomorrow? Yeah, let me put it to this tomorrow. Then if you struggle after this one, then I can still help you. Yeah, but let's maybe summarize the steps. Let's check. Let's summarize the steps here. You want the nth root of a number. First thing, step number 1. Let me call this algorithm. I don't know why my pen is lazy. Algorithm. Algorithm is a sequence of steps you should do to do a certain task. Is that right? So step number 1, maybe not really the first thing you must do, but you must have the argument, the modulus of set. You must have it. I'm just guiding you so that you can see what you can do. Must have the argument, which is in this case x squared plus y squared. I can use b squared to a squared. I hope you understand. Then number 2, you must have arg z, which in this case is tan second function y over x. This is power minus 1 there. That's that. Then, state number 3, you must express the form in which your Z comes. That is the formula. So now we can say now ZK is equals to, I will write the two formula. So first one I will say R that cosine. I will now not split it, I will just put it as the argument which you got from here. Let's call this theta, isn't it? Plus 2k pi,
Can I ask you?
that plus, just hold on a second, then I sine theta plus 2k pi over n, put that there, then let's close that, then we say here k equals to 0, 1, 2, dash, dash, n minus 1. Then in brackets there, we must produce n different roots. That's the thing. So I think up to there now, the manipulation of this formula, that's what we're trying to do in that example. Take 0, take 1, and work out your argument correctly and evaluate and get that thing. The last one, I can also, if you don't want, this is not very economic to you, then you can take this as that. I mean economic in terms of time and space you use to write that. This is more economic in terms of time and space, I think, but not that it's easy or is better than the other one. Then you write it like this, then the condition of k are still the same. Then that's that. So, you want to ask a question about this? Yes?
For the argumentative for number 2, do I always use 10 to the power 1x y of x
Yes.
for every modulus that I get? I'm always using 10.
For any number, complex number of God, you must use that.
But it's always 10, it's never going to be cos or sine.
No, 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 it cannot be cos. It cannot be cos. Do you understand how to use reference angles?
Yes, I do.
Reference angles, do you understand? Maybe let me just briefly just recap on that. I really wanted to record that. Don't you think so? Yeah. So I will summarize at the end, right? Now, so in this way, what we're trying to say, if you use this reference angle, you can either reflect it across here or reflect it across the y-axis, you get that on there. Then for that angle which you get there, we've discussed there is pi minus that. For angle you get there, you just reflect this angle across, you've got that angle there. For that angle which is from 0 here, round up to there, it will be this pi plus the reference angle which is there. Coming to the fourth one, it should be 2 pi minus reference angle. What do? You come from here, you go right round, you get to there, that's 2 pi. But you want this arm, then you must go negative, that's why we say 2 pi minus that. Now, somewhere there is a term called the principal argument. Have you read that? Principal argument. And they tell you that the principal argument must be a theta between minus pi and pi. Check there. One side is inclusive, the other one is not inclusive. You understand? Now check what's happening there. If I go this way, up to there, I'm pi. I've gotten pi, radians. But if I start from here, move this way, I come here, I don't touch line, I put an open thing there. It's minus pi. but I don't touch pi. I don't get to minus pi. I just go strictly above minus pi. So you get this kind of interval, isn't it? So now, what is this principal argument? Let me put here theta p for theta principal argument. What is this principal argument? It must be an angle for this, like this one. Then let's start from the first quadrant, this one, the reference angle. Is it a principal argument or not? Check. Is it less than pi? The reference angle for Z1.
Yes, it is less than pi.
So in the first quadrant, the argument coincides with the principal argument. Are we together? Let's go to this to the second number here. This angle. Is it less than pi? So it's still principal argument. So first quadrant, second quadrant, the very first positive arguments we consider are principal. Let's come to this Z3. Let's go this way. Pi. Am I allowed to go beyond this? Am I allowed to go beyond this? Look at this.
No.
It's more than. So then I discard that angle. It's not a principal argument. What I'm going to do? Because if I take the same from there and they come this way, that when I take that angle up to there, I get the same number. Or I get from 0 negative wise going there, I get the same number. Do you understand what I'm saying? So that angle is the one I'm going to consider as what? The principal argument. Same thing which has happened to the fourth quadrant. If I go to the fourth quadrant via this way, I've gone beyond pi. I'm not going to get this as principal. So I come here and start there and go backwards, then I get what my principal argument. So now if I'm going to write a number, a complex number, using the principal argument, this argument or just discussion we're doing here is very, very important. So now this number Z4, I'm going now to write it as this way. Z4 is going to be equals to R angle minus theta 0. Do you see that? What about this one? If I go minus this way up to pi, I'll go there. But this one, I'll go minus pi up to there plus theta 0, because I will have to go up to touch there and come back. That angle, reference angle, then that's that. Then this is the angle I'm going to use as my principal argument. Those are the two problematic ones. Otherwise, the first one and first quadrant and second quadrant is exactly the same thing. Is that clear, guys? Okay. So I hope you're going to be able to sit down and listen again and see whether you are getting exactly what you want. Yeah. So can I close that discussion there? Okay. So thank you for listening.